Hello everyone and welcome back to this course. So we were discussing about the Gibbs-free energy and its conversion to potential, and we also solved few numericals understanding how this potential or reversible cell potential varies with respect to temperature as well as operating pressures. So let's continue few examples and then we will proceed with the characteristic curve of fuel cell and electrolysis and the losses that are involved in therein. So, we will take with the same numerical that we discussed for the fuel cell, wherein we had assumed cell to be operating at 80 degrees Celsius with hydrogen and oxygen pressures at 3 atmospheres and 5 atmospheres respectively. So, we will take the same problem with respect to electrolysis now. So, let us have this electrolysis cell operating at, this is again example, operating at T equals 80 degrees Celsius and pressure of hydrogen is say 3 atmosphere and pressure of oxygen here now it is 5 atmosphere. So, please let us understand that in case of electrolysis air does not come out, it is the hydrogen and oxygen that comes out. So, it is a pure hydrogen and pure oxygen. So, we will see how this nurse potential or the cell potential varies slightly in case of electrolysis. Predominantly it remains the same, the process remains absolutely same. So, let us first write down our reaction. So, H2O that gets converted into hydrogen and half mole of oxygen. So, this is our reaction. So, also let us write down the enthalpies and the entropies for respective species. So, this is minus 286, these are all in kilojoules, or we can even write it in intrinsic form, kilojoules per mole. This is enthalpy of hydrogen and oxygen are 0 as they are assumed to be occurring in the universe in natural form. Entropy is 69.91 and for hydrogen it is 130.68 and for oxygen it is 205.19. So, this is in joules per mole per Kelvin and this is in kilojoules per mole, you can say, if it is on the intrinsic basis. So, let us first write down our equation. We have to find out the nurse potential. So, we have En, which is also I can write it as E at different pressure and temperature is Et minus RT by Nf ln of, now ln of, as you can say, if you people remember, our general reaction was A plus B, that is converted into M plus N. So, here in this case that ln term was on the the activity of M over M multiplied by activity of species N of it over its concentration divided by activity of A times activity of B times B. So, if you look at this ln term, the numerator is the products. So, that in this reaction it is M and N. So, we have to consider the products on the numerator side. So, if we come back to our equation, the products are hydrogen and oxygen. So, we need to consider the activity of hydrogen times the activity of oxygen raised to half, since we have the half molarity of oxygen being generated there, divided by the reactant species, which is the hydrogen water here in this case. So, this becomes our equation. N is 2 here and F remains the Faraday's constant. T is your operating temperature, which is 80 degrees, that is 353 Kelvin, and we have to now find out Et. So, Et is nothing but E naught plus entropy change of this that is incurred in this reaction times the temperature difference. So, T minus T naught, and as we can understand this entropy change is entropy change at STP plus integration of heat capacity, which is function of temperature, by T dt when it is varied from T naught to T. So, we have written the same equations again. So, our focus is to find out the Nernst potential, and subsequently we have to first deal with the entropy, and then subsequently we have to go to the ET, that is the cell potential for any arbitrary temperature T, and then will ultimately lead to the Nernst potential. So, let us start with our numerical. So, let us first start with the entropy. So, you have to find out the entropies of respective chemical species, that is hydrogen, oxygen and water. So, let us first start with the entropy of water. So, entropy of water is entropy of water at STP plus T naught to T Cp T by T dt. Now, this heat capacities, which is dependent on temperature, has to be again integrated with respect to water, and we already know what and how this heat capacity depends on the temperatures. We need to substitute that here again. So, let us write that up. Entropy of water is 69.91 plus integration of 298 to 353, and we have to write this Cp, which is 56.506 minus 22,222.6 times T to the power minus 0.75 plus 116,500 by T minus 56,070 minus 1.5. So, this is what we have by T dt. Let us solve this up. So, we will write this up again. Sorry, I made a mistake. So, this is not the Cp of water. Cp of water is 143.05 minus 58.04 T to the power 0.25 plus 8.2751 times T to the power 0.5 minus 0.03698 times T by T. So, let us go ahead and solve this 298 to 353. So, let us normalize this with respect to the T, which is at the denominator. So, it is 143.05 by T minus 58.04 times T to the power minus 0.75 plus 8.2751 T to the power minus 0.5 minus 0.0369989 times T gets cancelled. So, this is again dt, this is equal to 69.91 plus, let us solve this up. So, this is 298 to 353, this is 143.05 ln of T minus 58.04 T to raised to 0.25 by 0.25 plus 8.2751 T to the power half, T raised to half by half minus 0.03699 times T. So, let us go ahead. This is still 69.91. So, if we solve this up, this will be 24.229 minus 41.7212 plus 24 and 41 and then 25.249 minus 2.04395. So, if we solve this, this comes close to 75.632 joules per mole per Kelvin. So, this is the entropy of water at 80 degrees Celsius. Let us go ahead and find out the entropy of hydrogen now. So, entropy of hydrogen is entropy of hydrogen at STP plus integration of T naught, which is 298 to 80 degrees, that is 353 Cp, a function of temperature by T dt. So, entropy of hydrogen is 130.68 plus integration of the Cp over 298 to 353. Now, this is 56.506 minus and 6 times T to the power minus 0.75 plus 116500 by T minus 560,700 times T to the power minus 1.5 bracket complete dt, and this is whole divided by T. So, let us go to the next step, 130.68 plus. So, let us solve this. This is over 298 to 353. This is 56.506 divided by T minus 22,222.6 times T to the power minus 1.75 plus 116,500 divided by T square minus 56,0700 times T to the power minus 2.5, right. So, if we now substitute, sorry, there is dt here. Let us go to next slide. So, we will still write 130.68 plus, now let us say we have to solve the integral. So, we have, this will be 56.506 ln of t minus 22,222.6 into t to the power minus 0.75 divided by minus 0.75 minus 116,500 divided by minus t and plus 560,700 divided by minus 1.5 times t to the power 1.5, and this is still to be solved over these temperatures 353. So, if we substitute for these temperatures and we find out, this comes close to 130.68 plus 9.57067 minus 49.280 plus 60.911 minus 16.302. So, this is entropy of hydrogen at 80 degrees Celsius. So, if we sum this up, this comes close to 135.57 joules per mole per Kelvin. So, we have found the entropy of water we have found entropy of hydrogen. Let's go ahead and find out the entropy of oxygen, which is, we will write with the same expression or similar expression, entropy of oxygen at STP plus integration of Cp T by T dt over the temperatures, that is 298 to 353. So, now we have to substitute for entropy of oxygen at STP was, I think, 205.14. So, let me write this expression again and then we will substitute for Cp. Cp, which is function of temperature by T dt. So, let us substitute for Cp, which is 205.14 plus integration 298 353, it is 37.432 plus 2.0102 times 10 to the power minus 5 times T over 1.5 minus 1.78570 times T to the power minus 1.5 plus 23688800 times T to the power minus 2. This is whole divided by T dt. So, this is 205.14 plus, so let us solve this. This is 298 by 353, this comes 37.432 by T plus 2.0102 to 10 to the power minus 5 times T to the power 0.5, then minus 1.78570 times T to the power minus 2.5 plus 2368800 times T to the power minus 3. This is Tt. So, we have now taken into account the factor of temperature, which is our denominator. Now, let us go ahead 205.14 and then let us now solve it. So, this is our temperatures, this is 37.432 ln of T plus 2.0102 into 10 to the power minus 5 times T to the power 1.5 by 1.5 minus 1.78570 times T to the power minus 1.5 by minus 1.5 plus 2368800 by divided by minus 2 times T square. So, this is at temperatures 298 to 353. So, let us move ahead, we will solve this and it comes 205.14 plus 6.340 plus 0.019941 minus 0.000 51957 plus 3.8. So, this comes, this is the entropy of oxygen at 80 degrees, that comes close to 215.332 joules per mole per Kelvin. So, now that we have found out the entropies, let us find out the entropy of the reaction, which is, so entropy of the reaction is the entropy of products minus entropy of the reactants. So, entropy of product is your those two gases. So, we have to take into account their entropies. So, which is 135.1 57 plus half of 215.332, half, because we have half mole of oxygen being generated and 1 mole of hydrogen. So, that comes like this, minus entropy of the reactants, which is water. So, that we have 75.632. So, if we solve this entropy of reaction comes close to 167.604 joules per mole per Kelvin. So, as we can understand, this is the entropy of the reaction, which is a positive term. It is plus 167, which means the entropy of the system has been increased. And why is it so? If we look at this reaction that is involved, we have water being converted into half mole of oxygen and 1 mole of hydrogen. That means if we consider water is in liquid form, so liquid form of water is converted into 1.5 mole of gases. So, since there is a more generation of gases, as we have discussed this before, that entropy of the gaseous products, or rather number of moles of gaseous products are more compared to that of the reactants, the entropy of the reaction is likely to increase. So, in following the same principle that we have seen, that entropy is positive here, underlining the fact that there is more chaos in the system as and when the system undergoes this reaction. So, let us find out the ET. So, ET, as we know, ET, it is E naught plus entropy by NF times the temperature difference. So, here E naught, as let me write it here. So, we have done this calculation before. So, E naught is basically delta G naught by NF. So, since delta G is a positive minus delta G naught by NF, this is the equation, and this minus will be there. Delta G is a positive term for the electrolyzer. So, which comes close to plus 237,000 joules per mole divided by 2, N is 2, times F is 96,485 coulombs per mole. This is coulombs per mole. So, if we try to find out E naught for electrolyzer, this is for the electrolyzer. So, E naught comes minus 1.23 volt. This is at STP. So, as you can see, we have taken E naught. So, delta G naught, which means this is at the STP. So, if we substitute this here, so if we substitute this E naught here, it is minus 1.23 plus entropy is 167 is plus 167.604, N is 2, F is Faraday's constant, which is 96,485, temperature is 353 minus T naught is 298. We can also substitute this in degree Celsius, it does not matter because it is a temperature difference. So, the answer will be same. So, if we solve this up, this will be minus 1.23, and this is all positive term. We have positive entropy and the temperature difference is also positive. So, the final term will also be positive here. So, it is 0.0477. So, it is minus 1.23 plus 0.0477, that leads to minus 1.1823 volt. So, this is your ET, that is the reversible cell potential at 80 degrees Celsius for the electrolyzer. So, this is we have found with respect to equation 2. Now, we have to go ahead and find out the nurse potential when it is operating at 80 degrees and is generating hydrogen and oxygen at 3 and 5 atmospheres. So, let us start with let me write that equation again, E n, which is also as E pressure and temperature. The EPT stands for potential at arbitrary pressure and temperature, which are different from the standard temperature and pressure conditions. which is equal to Et minus RT by NF ln of products. So, products are the activity of hydrogen times activity of oxygen divided by activity of reactants, that is water. So, we have written this expression again. This should be raised to half, and so let us go ahead. So, let me write this up. For gases, as we have discussed, this activity of hydrogen and oxygen can be replaced, or rather it is equal to by their respective partial pressures. So, activity of hydrogen is partial pressure of hydrogen by P naught. So, we have seen this before. Partial pressure of hydrogen in this numerical is, it is a pure hydrogen that is coming out. So, it is coming out at 3 atmospheres and standard pressure is 1 atmosphere. So, this is 3, activity of hydrogen is 3. What is the activity of oxygen? It is the partial pressure of oxygen by standard pressure. So, this is at 5 atmospheres by 1 atmosphere, which is our standard reference pressure, which is 5. So, and we already know activity of water is 1, that is taken as 1. So, coming back to our equation, so we can write this as En equals Et minus RT by NF ln of, so activity of hydrogen, which is 3 times the activity of oxygen 5 into 5 raised to half divided by 1. So, this is our substitution for the activities. Let us further substitute. So, this is your En equals Et is minus 1.1823 minus R is 8.314 into T is operating temperature, which is 353, divided by N is 2. In this case, that is hydrogen and oxygen reaction, N is 2 times Faraday's constant 96,485 ln of 3 into 5 raised to half divided by 1, that is same. So, let us solve this up. This comes minus 1.1823 minus this entire thing. If we solve this up, this will be minus of 0.0289. So, both are negative terms, so they will get added. So, En is nothing but minus 1.21 volt. So, as you can see, what does this minus sign signify? It signifies that it is an energy intensive process. So, we need to supply roughly 1.21 volt of electrical energy to kickstart this reaction, and then only we will be able to generate the, you can say, hydrogen and oxygen. So, this is what we have come to an end, and if we compare this nurse potential of the fuel cell, that was close to 1.2 volt for the similar conditions. So, if you have a fuel cell operating at 80 degrees Celsius, having pressures 3 atmospheres and 5 atmospheres, and on the similar side, if you have electrolyzer operating at again the same conditions, we will have almost similar potentials for the fuel cell as well as the electrolyzer. However, in case of electrolyzer, the potential is always negative, meaning that the energy has to be supplied. So, with that, I think we will stop here and we will continue with the losses and the characteristic curve in the upcoming class. Thank you.